OK, so last time we talked about a bit of the history, especially how Poincaré, and later interpreted by Emmy Noether, introduced groups associated to a space. And we're going to study this semester the homology groups and the first of the homotopy groups. These are the ones that I mentioned Poincaré made up to try to make sense of Betty's numbers. So this is taking a manifold and looking for originally k-dimensional submanifolds and seeing how many of those you could choose before you made a boundary of a k plus 1 dimensional manifold. And I mentioned that that definition ended up not working, so Poincaré had to revise it. The homotopy groups, we're going to see the fundamental group. We'll define it today. So the trade-off is that these groups end up being very hard to define, or at least it takes us a while to define them, but then they're very easy to compute. These groups are trivial to define and impossible to compute. So so that's the trade-off, and what we're going to be talking about this semester. Then we started talking about homeomorphisms as being the actual topic that topology should be studying, classify spaces up to homeomorphism. And what we actually have tools for in this class is to try to classify spaces up to homotopy equivalence. So a homotopy, we saw, is a continuous family of continuous maps. And a homotopy equivalence between two spaces is a map for which you have a map going in the opposite direction, where for homeomorphism we would want these to be inverses. For homotopy equivalence, we just ask that the compositions be continuously connected or homotopic to the identities. Then we saw a construction called the mapping cylinder, where you start out with a map between spaces and you decide to encode this in a space itself, so that you just have to study trivial maps on complicated spaces. And in this case, you take the cylinder on X, and then you connect it to Y using the equivalence relation that everybody at the right endpoint gets identified with his image in Y. Right, and somebody asked me what I meant by this, and I was thinking that maybe I didn't completely answer the question. So let me remind you what we mean by an identification space in general. So if sigma is some topological space with an equivalence relation, then this is the set of equivalence classes we have an obvious map that just assigns to each point its equivalence class. And then we make this into a topological space by taking the largest possible topology for which this is going to be a continuous map. Right? So we declare that a subset here is open if and only if its inverse image is an open set here. Right? So we topologize by saying that a subset is open if and only if the inverse image is open. Okay, so this is an instance where we're doing that. Our equivalence relation is every point is its own equivalence class unless you're at one of the points x comma 1, in which case the equivalence class also contains f of x in y, right? Yes?
In general, how should we read that symbol, like the flattened U in the middle?
Oh, this is disjoint union.
Oh, okay.
Yes, thank you. Yeah, so yeah, you have union, but when we want to emphasize that the sets, let's say you had two subsets of R3, and maybe they overlap, so this union would be a connected set, perhaps. We use this symbol to say, okay, don't ignore how they're sitting in R3, just take them as separate sets. And then we started talking about cell complexes. And that's where I'll start today. But before that, are there any questions on last time? OK. Great. So let's start talking about cell complexes. So I started out with the example of the torus and its identification space, one of its identification spaces. So it's a wonderful fact that you can classify surfaces and build them up out of polygons. So we talked about how what this means is that this edge is identified with that edge and this edge with that edge. And so when you glue them together, you'll end up with a torus. But you can also think that what we have here is a vertex, right? And all of the corners of the square correspond to the same vertex, because once you glue these together, you find that they're loops. Right? Let's say that's A and that's B. So you ended up with loops. So since this is where A begins and this is where A ends, and it's a loop, it's the same point here. Right? And similarly, B begins and ends at the same point. So all of these vertices of the square correspond to a single point in the torus. The edges correspond to these two circles. And then the interior of the square corresponds to the surface of the torus, right? So how you should think about this for purpose of generalizing it is that you have a single vertex, which we're going to call a zero-dimensional cell. And then you have two one cells, these edges, and then a single two cell, which is the interior, right? So in general, a cell complex is any space that you build up inductively like that, right? So a cell complex is built up so you start out with a zero skeleton consisting of a discrete set of zero cells, so just vertices, just points. And then inductively, given the K-skeleton, you form the K+1 skeleton by attaching K+1 cells. So these are disks through cleverly named attaching maps. So let's say you call these A upper K+1, lower alpha, where alpha is some indexing set. Then for each alpha, we have a map from the boundary of the disk of dimension K+1 onto the k skeleton. Right? And then x k plus 1 is equal to xk, and then you add all of these disks, one per index along these maps. Right, so these k plus 1 cells, each one of them is a disk. And so I just need to know how am I going to glue this disk onto the space I've constructed so far. Right? And so we're going to glue it on by making identifications of its boundary with part of the set you already have. Right? So you just need to tell me how are you going to map this boundary into the space. So for example, here, you could think that you start with your 0 cell, then you put in these 1 cells, so the edges, and then you have to glue in this disk, the disk of dimension 2, and you just have to tell me how you're going to glue it. So here I would say, oh, well, you're going to glue it by attaching it the boundary, mapping the boundary to A, B, A inverse, B inverse. Right? And so that would tell you put the center of the square in like that. OK, so x is then the union over all of these. And we might have infinitely many cells, in which case you could worry. And we could have infinite dimension going on here. There's no reason why it has to stop. And so you could worry about the topology. We give this the weak topology, meaning that a subset is open if and only if its intersection with each of the pieces is open. OK, so that's what we mean by a cell complex. So why? Well, really because this is where our tools work. So when you want to prove something, for example, there's this wonderful theorem where you want to show that a map is a homotopy equivalence, right? And what you can show, perhaps, is that the way it acts on these groups is always an isomorphism, right? And you want to know, well, is that enough to say that the map is homotopy equivalence? And the theorem, the theorem for which these spaces were defined, is that if you're mapping between 2 cell complexes, then yes. So this is Whitehead's theorem, which we won't get to until next semester. But Whitehead's theorem says that if you have a map between CW complex, cell complexes, and it induces an isomorphism on all homotopy groups, then it actually was a homotopy equivalence. Right? And really the strength is that you have this inductive construction of your space. So you can do a proof by induction if you're working with a cell complex, where if I just give you a topological space, there's nothing for you to induct over. Right? So anyway, these are very useful, especially when we get to homotopy theory as opposed to homology. Okay. Perfect. So that is the second topic I wanted to cover from Chapter 0. As I said last time, I encourage you to read Chapter 0 on your own. It has things that will be useful later on and that don't fit into the story told by the text. OK, any questions on this? Yes?
So when we're building this, the k+1 skeleton from the k skeleton, these maps phi sub alpha are sort of specifying how we're connecting each one of the previous, the cells in the previous dimension.
Yes.
So when we get to the 2-dimensional case, like for instance the square for the torus, how do we deal with the fact that there are points on the boundary of the square that are a part of 2 different cells in the previous dimension? Like for instance, the corners of the square would be both a part of side A and of side B.
Yeah, but that's OK, right? So this is just a set, right? The K skeleton is some set that you're attaching onto, right? And it includes, in this case, when you get to dimension 2, it has the 0 cells and the 1 cells, right? So it's just the set that you've constructed so far, and you just have to map onto it somehow.
Okay, so x to the k is just a set of points at that point.
Sure.
Okay.
But with this structure.
Right.
Yeah. Yeah. Thanks. More questions? Okay. Excellent. So we can move on to the first real topic of the class, which is the fundamental group. Okay, so going back to our motivation, we want to detect holes in a space. And one way that we can do that is to think of a loop as being like a lasso, and then you try to pull it tight, and you see whether it gets caught on anything, right? So we introduced the notion of homotopy to make sense mathematically of this pulling it tight. And so now we want to just implement that. Put in a bunch of loops on a space and see if you catch anything. Okay? So let's start by talking about paths. So remember, our convention is that all spaces are topological, all maps are continuous. Right? So a path on a space X is just a map from the unit interval to X. Right? It could be any interval, but we use the convention as the unit interval. And we're going to say that two paths, well, let's say, are, let's say, path homotopic. If they are homotopic relative to the endpoints. So remember from last time, a homotopy is relative to some subset if nothing happens on that subset, if the maps are constant there. So what it means here is that there is a homotopy say H, 0, 1 cross 0, 1 to X, such that H of 0, comma S is equal to f of S, H of 1, comma S is equal to G of S, H of T, comma 0 is equal to f of 0 for all t, and h of t, comma 1 is equal to f of 1 for all t. Of course, these are for all s. Right? So we have a continuous family of paths that connects f and g with the property that the endpoints are fixed. Right? So the picture, of course, is that you have f doing whatever it wants and g doing whatever it wants, and we have a homotopy in between them, but the endpoints are fixed. Right? And we're going to denote this with a sub p for path homotopy, right? Just to emphasize that the endpoints are fixed. Okay, so we want to replace a path with a homotopy class of paths because we want to know if if there are holes, right? So we're going to be looking at loops in a moment. But one advantage, immediate advantage of replacing paths with homotopy classes of paths is that you can reparameterize and not change anything, right? So remember, reparameterization is just changing the way you go over the interval. Like maybe you decide to go very quickly from 0 to 1/2 and then very slowly from 1/2 to 1. But you're tracing out the same path. So we don't want that to count as something different if we're just trying to figure out if there are holes in our space. And path homotopy does that for us. So let's write that down. If phi from 0, 1, 0, 1 is a map such that phi of 0 is equal to 0 and phi of 1 is equal to 1, then f composed with phi is a reparameterization of f and f is always path homotopic to f composed with phi, right? And so we're going to prove this by just writing down a homotopy. So what we're going to do is we want to have some class of functions that starts out at the identity function and ends up at phi and doesn't change the endpoints, right? And it stays, say, in this square, 0, 1, 0, 1. The graph stays in the square, right? So no problem. All you need to do is take the convex combination of phi and the identity function, right? So you just take, let's see, I want it when t is equal to 0 to be there. So do that, and then t phi of s. Right? So what we're using is that on Rn, I have addition, right? And the square is convex. So if I take a convex combination, I stay in the square. And this is continuous, and it does what I need, right? When t is equal to 0, it's f of s, and when t is equal to 1, it's f composed with phi. That's worked out great, so let's do that some more. So let's note if you have any convex subset of Rn, and you have two maps, two paths in X, then these are homotopic, are path homotopic if and only if they have the same endpoints. Okay? So obviously, if they are path homotopic, then by definition of path homotopy, they have to have the same endpoints, right? But the cool fact is that if they have the same endpoints, then they are indeed path homotopic. And you can just take a convex combination to check that, right? So if you have the same endpoints, then this is a homotopy into X, because X is convex, right? It's continuous, and it starts at F and ends at G. And it's a path homotopy because they have the same endpoints, so this always has the same endpoints. Yes? Nota bene, important note. More questions? Okay. Okay, some more notation. If you give me any point in x, then let's denote gamma x naught be the constant path. Right, that just stays there. And given a path let f bar be the inverse path so just the same path done in the opposite order. Right. Okay, and then most importantly, given two paths, such that f of 1 is equal to g of 0, define the concatenation of f and g to be, so we'll denote it with f dot g. This is path in x so you do f twice as fast and then g twice as fast, just so that you finish inside the interval. Right? So you do f then g. Right? So important not to confuse this with composition. Right? There's no reason for composition to make any sense. And that's not what we're doing. But another good source of confusion is when you're doing composition, you would apply the function on the right first, and then you would apply the function on the left. That's not at all what's going on here. You're doing the path f first, and then g. Right? So it really is like concatenation. You're just chaining these things together. Okay. Okay, let curly p be the path homotopy equivalence classes of paths in X. Well, maybe let's say P of X. Right, so you have paths. These are just the maps from 0, 1 to X. And now we're going to assign to each path the path homotopy equivalence class. Okay, and I'm getting ahead of myself because I haven't shown that these are an equivalence relation. Right, so let's check that it's an equivalence relation. Right, this makes sense. Because path homotopy is an equivalence relation. OK, so we have to check three things to see that it's an equivalence relation, right? Every path should be equivalent to itself. That's easy. Take the trivial homotopy. If path is equivalent, if f is equivalent to g, then g should be equivalent to f. That's easy. Take the same homotopy between them. And so the interesting one is if f is path homotopic to g, and g is path homotopic to h, then f should be path homotopic to h. Right? So we need to check that. So yes. So let's say capital F be a homotopy between f and g, capital G be a homotopy between g and h, and then note that h of, what order did I use over there? T and then S. OK, so obviously all we want to do is run the homotopy F first, and then run the homotopy G. And you'll start at F, and you'll end it at H. Right? So we have to do the same thing we did over here. To fit it into the interval, just have it go twice as fast. Right? So the T is the parameter that goes in between the two paths. So we'll just have it go twice as fast in T. So this will be for T in 0, 1/2. And this will be for T in 1/2, 1. Right? And there we go. It's a continuous function because each of these is continuous. And at the endpoints, they match because they're both equal to G. Right? And it starts at F, and it ends at H. Right? So it does what we wanted. OK, excellent. So we have an equivalence relation. So we can look at the equivalence classes. And we're going to denote that by curly p of x. Okay. OK, so here are some properties. Here are how this operation of path concatenation works out for equivalence classes. So first of all, it's well defined. So if you have two equivalence classes of paths, well, I should start with. If you have an equivalence class of paths, then F0 and F1 are well defined. Right? So what I mean is you have an equivalence class of paths. You pick a representative, this F, and you look at its endpoints. Right? And well defined means that it didn't depend on the choice. Right? You can pick any representative here, and you have well defined endpoints. Right? And this is trivial from the definition of path homotopy. Path homotopy fixes endpoints. Right? So anybody in the class has to have the same endpoints. So now let's say you have two homotopy classes of paths such that f of 1 is equal to g of 0. Right? And it makes sense to ask this because by the first one, we know that the endpoints are well defined. Then we can concatenate by concatenating representatives, and that's also well defined. Right? So again, anytime we say well defined, it means that we've made choices, but the result doesn't depend on the choices we made. right? So in this case, the choice we're making is picking representatives, F and G, concatenating them, and then taking the homotopy class, right? Doesn't depend on the choice. OK, so you have a well-defined operation. And it is associative. You have trivial elements. So if you take F and you concatenate it with the constant path at the right endpoint, you get F. And if you take the constant path at the left endpoint and you concatenate, you still get F. And if you concatenate with the inverse path, you get the constant path at one endpoint or the other. OK, so this is really intuitive if you're just thinking of the picture, right? If you're looking, say, at associativity, so you have some space, and then you have one path given by F, one path given by G, one path given by H. I should have said here that, of course, this is only when this makes sense, right? When the endpoints work so that you can concatenate. So then the picture looks like this. And so you can think as a path, I'm just going to go from here to here by following F, then G, then H, right? And so both of these correspond to the same picture, right? But as maps, as functions, they're different because this one says spend half of your time doing H and the other half doing F and G. And this one says spend half of your time doing F and then in the other half do G and H, right? So as functions, they're different, but they're homotopic. And so we have equality once we've passed homotopy classes. Okay? So all of these, the picture should be clear. And it's just a matter of checking that the only difference in the maps is washes away with homotopy. OK. So let's prove this. We already did the first one. The second one, we have to check that this is well defined. So let's see, first one, check. Second one. So to see that this is well defined, we want to say that if you had chosen a different representative of this class and a different representative of this class, you would have gotten the same class here, right? So what we want to check is if F0 is path homotopic to F1 and G0 is path homotopic to G1, then we want to know is F0 dot G0 path homotopic to F1 dot G1. Yes?
So what's the F0? F sub 0?
F sub 0. So given two paths, just any two paths.
There's different representations.
That's right. Just so exactly. So these are going to be, since they're path homotopic, they represent the same equivalence class. So the question is just, if you have two different representatives, do you get the same? Do they represent the same class? OK, everybody happy with this being what we need to prove for this? OK, excellent. Well, just take, let F be a homotopy between F0 and F1 G homotopy between G0 and G1, and then just form F dot G. So just concatenate them, right? So this is a continuous family of paths, and this is a continuous family of paths. So just concatenate them for every t. And this is a homotopy between F0 dot G0 and F1 dot G1. Right? Maybe this would be clearer. I should have just used this notation. Let's do F sub t and G sub t. So then this is F sub t concatenated with G sub t. All right, a continuous family of paths starting at F dot G naught and F1 dot G1, ending at F1 dot G1. OK, so we have a well-defined operation, and now we want to check that it's associative. So let's just write down what this would be at the level of paths. So if I do F dot G dot H, right, assuming that the endpoints match, so this makes sense. What is this? Well, in half the time, we have to do F dot G. So that means in a quarter of the time, I have to do F. So it's going to be F of 4s, and then G of 4s minus something, and we'll work out what that is. So this is S between 0 and 1/4. Then here, S between 1/4 and 1/2. So I need to put something here so that when I'm at 1/4, this gives me G of 0. Right? But at 1/4, 4s would be 1, so I just subtract 1. Right? And then I want H in half the time, 2s minus something. And same thing here, I'm going to have s between 1/2 and 1, and I want to be at 0 at 1/2, so I have to subtract 1. Right? So this is what the concatenation would be in this order. Similarly, if you did this in the opposite order, then you would just be doing this in half the time. This in a fourth of the time, and this in a fourth of the time. This minus 1. No. 1/2, 3/4, and 3/4, and 1. There we go. H. Right, so it's just doing the same things, but at different speeds. Right? So you can see that that is just a reparameterization of this. Right? So these are reparameterization of each other, and hence they're path homotopic. Right? And so you see very clearly why we wanted to pass to path homotopy classes, because they're not associative on the nose, right? They're not associative as paths, but they are associative as homotopy classes of paths. Okay, and now just fun with the constant loops. So if you do f dot gamma f of 1 at time s, this would be do f in half the time, and then do nothing. So this is a reparameterization. of f. Right? Just do f in half the time and wait. Similarly, if you wait half the time and then do the path very quickly in half the time, this is a reparameterization of f. Right? And then if you do f and then go back along the same way you came, right? So we're going to show that this is homotopic to not doing anything. And we should think about it like if f was just go from here to here, and then f bar is, OK, now go back the same way you came. Well, we're going to get to a homotopy where you don't move at all by saying, well, don't go all the way before you start heading back. And don't go all that way before you start heading back. And eventually, we end up with a path that did nothing. Right? So let's just write that down. So let f sub t be the path. Well, let's write it down. So t of s is equal to f of 1 minus ts, I think will work. When t is 0, that's just f, and when t is 1, that's just f of 0. And in between, you're just going from 0 to 1 minus t. And let's say h sub t is equal to ft dot ft bar. OK? So f sub t is just one of these paths that goes along the same route as f, but just doesn't get as far. Right? It stops at 1 minus t instead of stopping at 1. Right? And so this h sub t is a continuous family of paths that starts at f bar and ends at the constant path that's just at f of 0. Right? So h sub t is a path homotopy. Notice that, of course, f sub t is a continuous family of paths where the endpoints are changing, right? Because it doesn't go all the way out to f1, right? But if I do f sub t dot ft bar, then the endpoints are always f of 0, right? It goes from f of 0 out some ways and then comes back to f of 0. So this is a path homotopy because the endpoints are fixed. Dot f bar and gamma f of 0. OK? Wonderful. And then just interchanging f and f bar yields a path homotopy between f bar dot f and gamma f of 1. OK? Which proves a lemma. OK, so a corollary slash definition. Right? For each x naught in x, let pi 1 be the homotopy classes of paths such that f of 0, so in p of x, such that f of 0 and f of 1 are both equal to x naught. OK? And the part as a corollary is this this is the fundamental group of X with base point X naught. Right, so the corollary is that this is a group. All right, the operation is concatenation. Right, all of the homotopy classes that we're looking at begin and end at the same point. Right, so it always makes sense to concatenate. The operation is associative because it's associative whenever the composition makes sense. And we have an identity element, which is just a constant loop that doesn't do anything. And we have inverses by just taking a loop and then running it in the opposite sense. Right? So we actually do get a group. Yes?
Can you just read what says all the way to the right?
Yes. So this says let pi1 of x comma x naught be the set of equivalence classes in P of x such that f of 0 equals f of 1 equals x naught. And this is the fundamental group of x with base point x naught. OK. So as a remark, what this lemma showed the lemma shows that P of x is what's called a groupoid. It's called the fundamental groupoid of x. Okay. In fact, something sort of stronger is true. This is like the canonical example of a groupoid. All other groupoids are things that behave like the paths on a space. Right, so the definition of a groupoid, which I won't write down, is exactly what we proved in the lemma. Right? Those are the axioms that a set with an operation with a partially defined operation should satisfy to be a groupoid. OK. But actually, we will focus on the fundamental group. Partly because we know what it means to compute a group, right? You have a list of groups that you like, and then you try to identify the group you're looking at with one of those on that list, right? And we don't have a similar list of groupoids, right? So, but for some theorems, to generalize some of the theorems we're going to see, the right language for it is the groupoids. OK, very good. So that's the definition of the fundamental group. Are there questions on the definition? OK, so our first example is a trivial one. So if X is a convex subset of Rn, then pi1 of X is trivial for any right, and that's because we saw that paths are path homotopic if and only if they have the same endpoints, right? And a loop at x naught has the same endpoints as the constant loop at x naught. So it's path homotopic to the constant loop. Right? Any loop based at x naught has the same endpoints has the constant loop, and hence is path homotopic to it. Right, and we've seen that the homotopy class of the constant loop is the identity element. So this group only has the identity element. Okay. So what about the base point? How important is the base point? Right? So most of the time, not very important. So if H is a path, connecting x0, x1, then it induces a map, let's call it beta H, from pi1 of x at x1 to pi1 of x at x0. Right? So what's the picture? I have a path, H, that starts at x0 and ends at x1. And then I want a map from here to there. So you give me a loop based at x1. I have to give you a loop based at x0. So of course, what the loop is first do H, then do that loop, then go back. Right? So you give me a loop based at x1, and I send it to first do H, then do that loop, then get back. Right? And of course, it's associative with homotopy classes, but just for the sake of definiteness, let's say you do that one. Okay, so we have this map, but of course these are groups, so we really would like to have group homomorphism, and in fact we'd like to have a group isomorphism, right? So let's check that this is. Right, so. Okay, so we should say a word about it being well-defined, right? But it's well-defined because we already checked that concatenation is well-defined at the level of the homotopy, the fundamental groupoid, right? So, so we already know that this doesn't depend on choice of representative. So now let's go directly to group homomorphism. So let's see if you have beta H of the concatenation of two equivalence classes of loops. So, okay, on the one hand, this is beta H of that loop, and that, by definition, is the homotopy class of H dot F dot G dot H bar. And so this is the homotopy class of H. Well, okay, so let's do it like this. So within the fundamental groupoid, I can separate these out to the individual paths, right? And here it's associative, so I don't have to worry about parentheses. And now I can insert H bar and H right? Because I know that as homotopy classes, they cancel out. And now we just put those together. We have h dot f dot h bar and that is beta h of f and beta h of g. Yes?
Excuse me, why do we need the parentheses for the H, F, G?
Here, well, because as a path, it's not associative, right? Concatenation is not associated at the level of paths, right? So it's really just pedantic, right? Because it doesn't matter which path you choose, because at the level of homotopy classes, you get the same one, right? But it's just for the sake of being definite about which path we're taking. Yes?
In the last line, are those equivalence classes that happen to be?
These are, thank you, yes. Okay, and now we want to show that it's a group isomorphism. So what we'll do is define an inverse map. And of course, the inverse map is if you have a loop at x0, you get a loop at x1 by doing the same thing with the inverse path. All right, so to see this is an isomorphism, we check that beta h bar, which goes from pi1 of x at x0 to pi1 of x at x1, is an inverse. So beta h bar composed with beta h of the homotopy class of a loop is equal to beta h bar of h dot f dot h bar so that's h bar dot h dot f dot h bar dot h, and we know that this is the same homotopy class as the concatenation of the homotopy classes, and then these guys cancel, and you get f. Right? And similarly, h composed with beta h bar is the identity of pi1 xx0. Okay, so we have a left and right inverse. So it's an isomorphism. Okay. So what's the conclusion? Well, we don't really care about the endpoint as long as you can connect 2 points. Right? So, of course, if you have a disconnected space, then you're going to have a different fundamental group, potentially, of each connected component. Right? They don't talk to each other, because the loops based at one of the points won't see the other connected components. But as long as you can connect things with a path, then you get the same group up to isomorphism. Right? So, if any 2 points can be joined by a path, right, which of course is called x is path connected, then pi1 of x x0 is independent of x0 up to isomorphism. So often denoted just pi1 of x with or without parentheses. Right, so we leave out the base point if we're working on a path-connected space because we don't care. We get the same group. Right? But it's always implicitly there. The loops have to be based at a point so that you have an operation. OK, questions? OK, I think we're ready for first computation. Make sure.
Sorry, what's the N? So often
Denoted. OK. OK, here's a definition. A space X is called simply connected if it is path connected and the fundamental group is trivial. OK, so our only example so far, a convex subset of Rn, is simply connected. Right? It's path connected and the fundamental group is trivial. Right? And the name, simply connected, comes from the fact that this has the same property as convex subsets of Rn. Namely, two paths are going to be homotopic, path homotopic, if and only if they have the same endpoints. So if X is simply connected, then two paths in X are path homotopic if and only if they have the same endpoints. OK, so tonight. So just like in the case of a convex subset, one direction is trivial. If they're path homotopy, then they have to have the same endpoints by definition of path homotopy. So the interesting direction is, let's say they have the same endpoints, show that they're path homotopic. Right? So, OK, if you have F, and then you have G, and they have the same endpoints, right? Well, the information we're given is that the space is simply connected, so the fundamental group is trivial, right? So, OK, I want to say something about the fundamental group, and I have these paths. Well, they do have the same endpoints. So if I were to go along F and then go back along G, I get a loop, right? And I know that all loops are homotopic to the constant, right? So we know F dot G bar is path homotopic to a constant. In this case, F of 0. Right? So great. So we want to show that these are path homotopic. Well, F is path homotopic to F dot G bar. No, I want to start with G, I guess. G is path homotopy to F dot G bar dot G, because this is homotopy to doing nothing, right? And then this is homotopy to the constant loop G at G1, and that's homotopy to doing nothing, so that's F. Right. these are all path homotopies. Okay, so that's why it's simply connected, simply in the sense of there's only one way of going from a point to another. And of course, really, it's only one way up to homotopy of going from one point to another. Okay? Questions on this? One place where you might remember seeing the notion of simply connected is if you've taken complex analysis or if you've taken a good multivariable calculus course. Yeah, so if you have a simply connected, for example, the integral along f, assuming you have a function you can integrate and everything is nice enough, is going to be the same as the integral along g, because it's going to, well, because they're path homotopic. Yes?
The subscript is G of 1, right, on the gamma?
Yes, gamma of G1. Yeah. Okay. Okay, so the first non-trivial fundamental group we're going to have is for the circle, right? And again, if you've taken complex analysis, then you studied the winding number of a path around the origin, right? So that turns out to be a computation of the fundamental group of the circle. But we're going to do it a different way that'll generalize to the notion of a covering space. So the fact is that the fundamental group of the circle with any base point, so I won't bother, is the integers, right? And so to a loop, we're just going to assign how many times do you actually make it around the circle with sign, and that's going to determine the homotopy class. Okay, so right now I'll just tell you how we're going to do it, and then we'll actually do it next class. Right? So the trick is that you have this wonderfully behaved map from the real line to the circle. Right? So you can think that you have a circle, and imagine the circle is a bunch of rope that you've, you know, it's like your Apple cord that you wrapped around the charger, right? And then you pull it out, and what you end up with is a helix. Right? And if you had an infinite cord, then that's what you would get the whole real line lying above the circle. And every point on the circle has an infinite set of preimages sitting above it. Right? And the beautiful thing about this map is that if you have some path on the circle, like a loop, you could choose any one of these points lying above it, and then once you've made that choice, there's a unique lift of your path, right? Because let's say your path here and starts going this way, and you choose this point, right? So okay, the beginning goes up to here. And now I start going this way. Well, I have a whole interval here that's identical to an interval there, right? So whatever my path is doing at first, I just do that here, right? And then once I get to somewhere at the end of this, well, I have another interval that's the same as the interval over here, right? And so I can keep going around. And let's say this path just went around the circle once. I keep lifting on little intervals, and everything's going along great up here. I have no choice. But when I get back to where I started down here, over here I've gone around once and come up to the next point, right? So if you want to know for a path down here, you follow the path, how many times did you go around the circle, you know, with sign, right? Well, if you look at the problem up on R, then it's trivial because you lift your path, you have no choice once you've chosen the initial point, And you end up above the point where you started, but it doesn't have to be on R at the same point. It could be a different floor on this helix, right? And so then how many times did you go around? It's just how many floors did you go up or down, right? But R is simply connected. So all paths are homotopic as long as they have the same endpoints. So it's going to turn out that the homotopy class of a path here is really easy to see up here. It's just what floor did you end at, right? And there are an integer worth of floors, and so you get integer as the fundamental group. OK, so that's what we'll do next time.